This lecture is about the additional assumptions we need to make for the paired sample in the independent samples t-test. So the paired samples t-test is very similar to the one sample t-test because, like the one sample t-test, we're just comparing one column of data or one sample to a distribution that has mu of 0 at the center and from which we estimate the spread. But you'll remember that the big difference is that we're figuring out the difference scores. So we're actually having our data in pairs, like before-after scores, or related individuals like mother-daughter, and we're calculating the difference between those pairs of scores to use for our test. And so the first assumption is the same. The dependent variable is continuous. The second assumption is that we use paired measurements. We use independent difference scores. We have approximate normality and an absence of outliers. So you'll recognize a lot of these. So assumption 1 we've already discussed, but assumptions 2 and 3 look a little different in this test. So assumption 2, we have pairs of scores. So that just means these data come in pairs. We talked about natural pairs like two sisters or husband-wife or two roommates, but each person is systematically connected to another individual in this example. Or we could have two scores for each individual, like before-after scores, pre-post scores, or just each individual produces two scores in different conditions. And we also talked about matched pairs in which the researcher matches individuals according to predefined criteria. So that's the first assumption. We need these paired data points. And then the second is that the difference scores are independent. And this means something similar to what it does in the one sample t-test. So difference scores for one pair don't cause any change in difference scores for any other pair. For example, excuse me, if we're interested in measuring some sort of a conflict style in husbands and their wives, we'd have paired data, but we'd want to make sure that couples don't observe other couples having a conflict because it could impact their own responses and they would no longer be like a random sample of pairs of individuals. So looking at assumptions 4 and 5, also similar to the one sample t-test, we need to have approximate normality and an absence of outliers. So in this case, the data for the difference scores must be approximately normally distributed without outliers. And we know that we meet this assumption if n is greater than 30. We know that we meet this assumption if the population is known to be normal. And if the population isn't known to be normal or we don't have more than 30, we can check for normality. We can take a peek at the histogram. We know that we can't always tell that much from the histogram, but we can tell if there are any big deal outliers that stand out. We can take a look at the QQ plot. The points should be on that straight line without an S shape or a C shape. We can calculate the skew and the kurtosis scores and make sure that they're near 0 in Excel. And we can get the Shapiro-Weld test statistic W, and we are looking for a score that's near 1, and we want our p-value to be, notice the sign here, greater than 0. We want to fail to reject the null hypothesis. Because if we rejected the null hypothesis, that would mean that our data is significantly different from a normal distribution. The assumptions for the independent samples t-tests are just like the ones we've just looked at, but we add one more assumption. And remember, the independent samples is when we're comparing the difference between two mean scores with a null population for which mu is 0 and standard deviation is estimated from the sample. So we check for normality in the same way. I just read all of this a moment ago when we were looking at the paired samples t-test, so I won't read it again here. So what is homogeneity of variances? This is a new term. So all this means is that the variance between the two samples should be similar or approximately equal. And in this case, this would be our estimated variance, our EVAR. And so they're not going to be exactly equal. They're going to be kind of equal. So just some terms before we look at some images. Homogeneity of variances means the same thing as you might see it written sometimes as homodiscasticity. So if you ever run into this word, you know that it means the same thing as homogeneity of variance or equality of variances. They all mean the same thing. The assumption is that the spread of scores around the mean should be similar across both groups. And the rule of thumb is if we divide the larger variance by the smaller and we get a number less than 4, we're probably okay. But that's just a rule of thumb. We're always going to test it a little further. So looking at this example, here we can see group 1 and group 2. The histograms are using the same range on the x-axis from -10 up to 15 in group 1 and from -10 up to 15 in group 2. We can see that the means for these two groups differ. It looks like the mean for this group 1 is around 0, and it looks like the mean for group 2 is around 5. Both of these histograms look kind of normal. I don't see any distinct outliers, so it looks pretty good that way. And we can see that the distribution in each appears to be similar. Neither one appears to be spread out more than the other. If we look at the range of scores, from the lowest to the highest, we could see that, here we have, approximately -7 all the way up to 5, a range of 12. And here we have, just below the 0, maybe a -1 up to an 11, also a range of 12. And these would be considered equal. We could check it with our rule of thumb and take the variance for this second group, 4.4, which is the larger of the two, and divide it by 4, which is the variance for the smaller variance of the two groups, and we'd get a quotient of around 1, which is lower than 4, so that would be okay. In the second example, we have variances that are really not equal enough. Like the other pairs of variances, we see that the x-axis on each display is the same. Both x-axes range from -15 up to 15. But we can see the spread here is very, very tight for this first distribution. We can see that the lowest score appears to be around -2 and the highest score is around +2, a range of only 4. The data are tightly clustered around the center. It appears that the mean is around 0, but we can see this is a very small spread. And we could compare it to the group 2 on the right and see that we have, even though the mean might still be around 0, we have a much larger spread here. And this means the variance is going to be much larger. And so we can see that these two would not be equal enough. We could use our rule of thumb to check it and take the larger variance, 16, divide by the smaller variance, 1, and our quotient would be 16, way too big for our rule of thumb. So we are going to, in addition to looking at the images, we're going to check for homogeneity of variance, and we're going to use a test called Levine's test. We won't be doing it in Excel. We'll be using a tool similar to what we did for the QQ plot and the Shapiro-Wilk test. We're going to be comparing the average absolute deviations between the two groups. And all that means is when we calculate the deviation for the process of finding sum of squares, we square the deviations to get rid of the negative sign. What we're going to do here is find the absolute value, m minus mu, without the sign. And if those, and then we're going to run a statistical test. We're going to run a t-test using those absolute deviations. So we're not going to do it because we're going to call on a tool to do it for us, but that is what the test is doing. It's seeing if those absolute deviations differ significantly from each other. And if they do, if it's significant, if we reject the null hypothesis, then the sample would violate the assumption of homogeneity of variances. So what if you can't assume equality of variances? What if you find out that your data doesn't meet that assumption? Well, first off, if it does meet the assumption, then you're fine. You can use the independent samples t-test, and you'll do that test using the variance pool, the pooled variance, or var pooled, the way we've learned. But if you find that your variances are significantly different, we use a different test called the Welch's t-test. And the only difference in the t-test is that we don't pool the variances. We use each group's own variance estimate. But to make up for the problem, we adjust the degrees of freedom. And so we're going to have a more stringent cutoff point is, in essence, the consequence of that. And this is the formula here. I'll show you what that looks like in terms of the actual calculations. So to summarize these additional assumptions, we can find that in the paired samples t-test, like the one sample t-test, we need a continuous variable. Here we need data in pairs that are independent of all the other pairs, and we need a normal distribution without serious outliers. In the independent samples t-test, we need, like the other tests, continuous variables. We need two samples that are totally independent. The individuals in each sample are unrelated to each other. The data for both samples are normally distributed without serious outliers. And then here's that new one, that homogeneity of variances. The variances are approximately equal, and we'll use that Levene's test to test that.